He has been doing research in clean energy conversion and storage for 10 years, working with molten salt and solar thermal systems, lithium ion and flow batteries, and carbon dioxide electrolyzers. He received his Bachelor of Science in Mechanical Engineering from the University of Tulsa, his PhD in Chemical Engineering from the University of Oxford, and recently completed a 2-year postdoctoral appointment at the French Atomic and Alternative Energy Commission. He is now helping lead an effort to develop an open source flow battery as part of the Flow Battery Research Collective. I'll hand it over to you, Kirk.
Alrighty. Thank you, G, and thank you, Athena, for having me. Um, Always excited to tell people about this project that we're up to. This started as a part-time, it's still kind of a part-time volunteer project, but essentially we're a group of people that were interested in energy storage technology and met on the internet. I found Daniel Fernandez Pinto's blog where he was doing some open source battery work, and we teamed up. And then Professor Sanli Fayez, who's based in the Netherlands, joined. And so it's been kind of like a snowball, but we're all people who are interested in sort of motivated by clean energy transition and the bottleneck of energy storage that comes with that. So we're taking one particular approach to trying to do the R&D on this technology in the open. So I'll just go through some snapshots of where we're at, some context, and where we're trying to head to. Okay. It's frozen. I think it's because I have annotate. Okay. So I've already explained this, but yeah, the primary application of the type of technology we're developing is storing intermittent renewable energy like wind and solar. We're doing this right now. We don't have a legal entity. We're just a group of people on the internet. We have met in person, so I'm not getting catfished by researchers, but all of our research outputs are free to access, and they're explicitly licensed to allow for commercial use. So if we do end up making something that is like useful at a practical level, it's totally encouraged for a company to take that and manufacture it for profit. Just for reference, you probably are more familiar with lithium-ion batteries than flow batteries. So this is just a simple schematic of a lithium-ion cell where you have a positive and a negative electrode separated by a separator and a liquid electrolyte. And the principle of this battery is that you have a crystal structure on the negative side, usually graphite, some lithium oxide crystal structure on the positive, and you're basically, it's called intercalation. So these lithium atoms and ions are being like basically jammed into and out of these crystal structures reversibly. And this is a cross-section of a lithium-ion cell. It's really a feat of modern engineering. You can see down here on the lower right, the scale 50 microns. So like a few widths of a human hair, I believe. So essentially you have, like in that schematic, a crystal structure anode, and then like current collectors that allow for electrons to be transported into it, and then these repeating units of like the anode, separator, cathode, and then the other current collector. And so this is something that you could like, I guess lithium ion isn't necessarily open source, but there's a lot of intellectual property, a lot of trade secrets, but they're just very complicated to manufacture compared to a flow battery. Our flow battery research we're doing in home lab type settings, in like hacker and maker spaces, and there's just no real feasible way to build a lithium ion cell in that. You need more advanced chemistry, material science equipment. So unlike lithium ion, a flow battery, you actually store the energy not in a crystal structure, but in a liquid electrolyte. So you have a positive side and a negative side. And you have this basically tank of liquid electrolyte that you pump continuously through a reactor. So it's really you can think of it as like a small closed loop chemical plant. The volume of the liquid in the reservoir is proportional to the amount of energy that's stored in the battery, and the surface area inside this reactor here correlates with the power. So that energy and power are decoupled and totally independent of each other, unlike lithium ion or lead acid. So that's why these are envisioned for use more in grid scale, like long duration type storage, because you can continually just make you can keep the stack, what we call this reactor, the same size, make the reservoirs very large, and then you can have like a very long discharge time. Whereas for a lithium ion cell, you run into constraints of making those electrodes very, very thick, and it's hard to access that energy. And so, yeah, so you pump the liquid through like a porous electrode that's in contact with the graphite plate. And then you have redox reactions and some ions that are transported between the two sides. And so this scales in energy by increasing the size of these tanks, but and increasing the area of the stack. But this is just a unit cell. So a real flow battery will have, to increase the voltage, you will put multiple of these porous carbon electrode separator graphite plate assemblies in series, back to back with each other. And that's why we call it a stack. So that would look something like this. So you still only have two tanks and two pumps, one for each, the positive side and the negative side. But then these plates and electrodes and separators, you stack them in series. So electrically, everything is in series, but you have fluid manifolds that connect to the inlet and outlet of every positive and negative half cell. And those are all hydraulically in parallel. So it's a lot more plumbing and fluid mechanics and kind of mechanical engineering than you would find in like a typical lithium ion or lead acid battery, because you have this flowing liquid. So just to give you an example of like what these look like, there are companies out there that manufacture these, usually at like utility scale, but on the left here, we have RedFlow. This is like a home battery scale, kind of similar to like a Tesla Powerwall, 3 kilowatt, 10 kilowatt hour, zinc bromine. They actually like just went out of business a few months ago. And then on the right, this is like the largest, I think it's a rendering, but it's does exist, the largest flow battery in the world in China, just like could power a town. It's extremely large scale. So this is just to show you that there's a wide range. We're definitely trying to get closer to something that is on the left than on the right. So this is a kind of a just heuristic kind of comparison between the chemistries, just to kind of show you the pros and cons. So this is assuming you made everything at like, the same manufacturing scale, but flow batteries have simpler assembly techniques. It's more injection molding, plastic welding, making water, like dissolving inorganic salts in water is the electrolyte procedure. You can do it at scales smaller than a lithium ion gigafactory. Because they're water-based, depending on the electrolyte, they're generally much safer and sustainable. There's no fire risk. For cycle life, because you don't have like liquid, usually you don't have liquid solid conversion or intercalation of atoms like in lithium ion. This causes some irreproducibility or irreversibility over time with lithium ion and lead acid. With flow batteries, everything is a liquid all the time. And so in a well-designed system, they can last much longer and be cycled to like 0%, 100% state of charge repeatedly without negative consequences that you might find. So everything in engineering has trade-offs, however, and so the power density and energy density in terms of kilowatt hours per cubic meter or per square meter of floor space is generally lower than lithium ion or lead acid. So these are purely for stationary applications. This is where we are right now. So we have like a benchtop cell that's more for, we call it our development kit. So with this, we're hoping to decrease the cost and have a well-documented system that will kind of lower the barrier for um, researchers around the world, also enthusiasts, educators to experiment, to teach, to get involved in like flow battery development. And then by mid-2025, we're hoping to go to a large format cell. So increasing the area of that cell, but still not stacking anything in series. We'll be messing with the cell geometry, operating conditions, the flow, and then at the end of the year, we hopefully we'll have our first demonstration unit where we actually do start to stack this large format cell in series. So this is what our current benchtop development kit looks like. So we have positive and negative electrolyte reservoirs and pumps. The connecting tubing isn't shown. And then this is the cell here where you can see the positive and negative tabs. This is an exploded view of that cell I just showed you. So we have little tie rod bolts that hold it together, but from right to left, we have this end plate, copper current collector, a graphite current collector that sits on top of that, one of many gaskets, and then we have this white part. This is plastic, and it has these barbed fittings on it. That is where the electrolyte actually goes in and flows through and then flows back out. Then another gasket, and then this small black square, that is the graphite felt. So that's porous and electrically conductive. So you can flow a liquid through it and then do a reaction on it. And then in the very middle, this blue and gray part, that's the membrane that separates the positive side from the negative side. Then on the other side, you just have everything repeating in the opposite order. And then it's basically just like making a sandwich. And then when you assemble it all, it looks like this. Again, you can see here one of the 4 fluid connections. So you'd have fluid coming in, coming out, and then the same on the other side. Then you make your positive, negative electrode connections here. And then on the back, we just have the pump motors for these peristaltic pumps, an Arduino and a motor driver so that we can adjust and play with the speed of the pumps. So this is what the front looks like. The renderings are nice, but this is what it looks like in use in the prototyping stage, running some tests actually. The first chemistry we're using is zinc iodide, but like the design of the physical hardware and the chemistry is kind of a bit decoupled. That's the advantage of flow batteries, is that you can fill the tanks with a lot of different things. So those are kind of 2 different directions. We're focused less on the chemistry side, more on the hardware. But this is we picked this chemistry for a couple of reasons I'll show you, but just to describe how it works. On the negative side, this is if you're discharging, we have metallic zinc. So it's actually a hybrid flow battery. I can, if you have questions about that, I can ask them later. But so we strip zinc into zinc 2+. On the positive side, we have triiodide, and that gets reduced. So that's iodine, and then that gets reduced to iodide. And then the overall cell reaction here, and it's about 1.3 volts per cell. There's also side reactions. So if you have like oxygen coming into the system, it can react with some of the iodide and increase the pH a little bit, which we don't want. So why zinc iodide? So vanadium flow batteries are probably the most common commercially, but outside of a professional laboratory setting, it's very hard to source vanadium. Also, it's toxic. So not to say that zinc iodide is perfectly harmless, but it's a lower risk, easier to source, so lowering the barrier to entry. We can use really cheap separator membranes in the middle, like just paper even, actually, like off-the-shelf photo paper, as opposed to other chemistries where you need like a really expensive ion exchange membrane, like for example, Nafion. This chemistry is kind of like self-healing. So if you have a zinc chemistry, you will make dendrites, which can like pierce a separator However, with this approach, it reacts with the iodine and kind of self-heals. So it's very robust. And there's lots of interest in all iron flow batteries. However, these have really significant problems with hydrogen evolution, and this zinc iodide chemistry is manageable. So we don't need any additional systems to do tests. And we get like acceptable results for off the shelf. And we don't need additional strong acids or bases. And like I said, low toxicity, but please don't drink it. So this is just an example of the data that we can generate with this cell we built. The chemistry is in the caption. It's based on zinc chloride and potassium iodide, as well as a buffer to kind of regulate the pH. And so in the top left, you can see like charge curves. In subsequent cycles, you can see what dendrites look like in the current in the voltage data, these spikes here, but that doesn't like destroy the battery. And then the discharge curve here, which is happening at a lower voltage. So we can plot in orange the energy efficiency. So again, this is a trade-off. They're slightly less efficient than lithium-ion batteries. Although right now we're not really concerned with the efficiency, we're more trying to make a stable and repeatable system. This is just, yeah, showing you some of the noise that we have. But so we're getting like, this is all happening outside of a professional lab. Again, we were trained in academia, but now we're working in a resource constrained environment. And so we're hoping that others can reproduce this, around the world. And this isn't just the same chemistry, but a bit more concentrated, just showing that we can go to higher energy densities. As you can see, there's fewer cycles here though, because here we broke a pump. A lot of the issues in building these batteries relate to not super interesting fundamental science questions, but more like it leaked, or we picked the wrong tubing material that works for 100 hours and then fails at the 101st hour. So that is the kind of practical stuff that we're trying to debug and do so in an open, transparent way. So as we kind of grow from the benchtop to the large format cell and then finally start stacking those, we need to go from like peristaltic pumps, which are used for, aquarium, hydroponics, to actual centrifugal pumps that are very efficient but much larger. So that's where we're at right now. I've just sourced these chemical magnetically driven pumps that are 100 times faster flow rate than our old cell. And this is not our setup. This is from an academic paper from Kaki and Das, but this is an example of the type of setup that we would be going to. So you'd have, just like in that dev kit, tanks, pumps, and a flow cell potentially stacked in series. However, everything is much bigger. So initially, we'll probably build this system and just run water through it, so there won't be any chemical risk. And then once we have things proven with the dev kit, then we can one by one introduce the components into the large format cell, and then eventually the stack. So there's a lot of ways that we're trying to get people involved. We have an online forum that we've just launched. But we're really looking for people to try to build the kit using our documentation, give feedback, even just like reading the documentation and giving feedback. Does it make sense? Test some of the 3D printed components. Most of our cell, with a couple of exceptions, can be 3D printed. Also, we'll be designing the geometry for those flow frames for the large cell. That'll involve some CAD, and we would like to have some contributors with FEM or CFD skills, as well as getting into the battery monitoring system that will need to include some pump control schemes. So here's a link to our website and our forum. And then I'd like to acknowledge Josh Hauser, master's student at Utrecht University, and Professor Stanley Faez and their Fair Battery project, who've helped us out a lot. Daniel Fernandez Pinto, who's been doing all the chemistry. He's based in Valencia. And NLNet's NGI0 Entrust Fund, who's supported us with our first grant. So, and here are the references just for the record. So thanks for having me. And yeah, very open to any questions you all might have.
Thank you, Kirk. Yeah, and if anyone has questions or comments, please feel free to come off mute and ask away.
I had a question. Yeah, thanks for the presentation. I was wondering what kind of how much flow rate do you need for the battery to function? Like what kind of pressures are you building with the pumps? And also is there like is isolating the charge in the fluid a concern?
So just for example, this cell, these pumps are, I think they do around 60 milliliters per minute. And this cell area is 2, and we could increase it to 5, probably, or 10 square centimeters. That's probably too much. That's probably too fast. Generally, you try to have, there's a minimum like linear velocity through this cell. So the electrolyte comes in through here and it goes, this graphite felt sits here and you flow through that. And that generally you want to, in the free volume, you want it to be like 0.4 centimeters per second. Just for flow electrochemical reactors, that's considered like a good mass transfer rate. So it depends on like the thickness of everything. These pumps here are 6 milliliters per minute. They're probably not the most efficient ones you can find. But and this is like ambient pressure or maybe a few millibar above. It's not like a pressurized system. The only head to overcome is through this basically porous media and minor losses through the tubing and fittings. This is 6 milliliters per minute. I believe one of these pumps is around 6 watts. And the rule of thumb for like an optimized system is your pumps should be consuming no more than like 2% of the round trip energy efficiency. So with like 2 6-watt pumps, you'd be at like 1 or 2, you'd be able to build a battery of like a couple kilowatts. And as far as storing, I'm not sure I understood your question of like storing the energy in the liquid, but so for example, for the positive electrolyte in the zinc iodide cell, in the charge state, it's well, yeah, this is a bit different because so in the discharge state, we have potassium iodide, so we have these 3 I minus. Then we oxidize it and reduce I minus to iodine, which is like I2. So this I3 minus is actually like you have 3 iodine molecules in a iodide molecules in a line, and the net charge is minus. But both of these are like dissolved in the liquid the whole time. You can also have, for example, here you could have iron 2 plus and iron 3 plus, which like there are commercial solutions where you're just changing kind of the oxidizing or reducing power of the solution. It's not like potassium iodide pills that obviously you wouldn't take this, but like if there's a nuclear incident, you take potassium iodide, that's I minus. If you have like a wound and you put like iodine tincture as disinfectant, that's I2, which is the oxidized form. So there is no like inherent risk in storing that energy in the liquid form, just that the liquid does it does become more reactive. So you have to usually make sure everything is basically plastic that doesn't react. I don't know if that answers your question.
Yeah, gotcha. Yeah, thanks. Appreciate it. Interesting.
Any other questions? All right.
I have one question, but it's really broad. Do you have, is there like for you, is there a desired application for these batteries? Or kind of on the other end of the spectrum, are there like wild ideas that you have for, I guess, stretch application?
I think the main application would be like at the scale that's like imaginable for us. We think we could get to like a prototype that could be close to what you would have for like a home residential storage application. So say like 1 or 2 kilowatts and maybe 10 kilowatt hours would be, on the order of like what a lithium ion home battery could do. Obviously, there are bigger ones and smaller ones. But we wouldn't be like, as our entity kind of maybe grows and evolves, like we're not planning in this is like for R&D. And if we made a prototype that was like looked like it would make sense to manufacture, that would be done by like another entity. Maybe we would be involved with that, but that like we are not necessarily expecting people to like self build a home battery and connect it to the grid. Someone might do that. That would be awesome, but we're trying to kind of, I guess, do like technology transfer in a way. There's a lot of companies that are working on this, a lot that are going out of business because there's a lot of pressure from lithium ion. So we're trying to maybe sidestep some of that market pressure and get to like a more applied state and then maybe see if it could make sense for there. But I think like I'm really like, I think we need centralized energy storage as well. And like, there's a lot of value in like large battery installations next to a wind farm or something. But I personally am really interested in like more distributed storage. So more maybe pairing with like rooftop solar to allow for increased, self-consumption of energy. And especially in the last year or so, virtual power plants have really kind of taken off, where you have like a network of batteries that are all managed centrally, but geographically distributed. And I think, it would be awesome if a system that we maybe develop the foundation for could eventually be used for something like that to help facilitate a cleaner grid. Robert?
Hey, Kirk. Great presentation. So we actually do rooftop wind. I'd love to connect with you offline on some of this because I think we might be able to help, especially with what you just talked about with distributed storage and stuff. So
Great. Thank you. No, that's great to hear. And even just like hearing from like what people actually need, because some people like don't care if it's lithium ion, if it's flow battery, but it is safer. There's potential to be more sustainable, more recyclable at the end of life and last longer. So kind of going back to this, a lot of the biggest criticisms we get are, well, like lithium ion is cheap now. So like, who cares? Which is like valid. And because lithium ion has really come down in price over the last 5 years, extremely so. But lithium ion has been optimized for portable applications, for cars, for phones. And it works for stationary storage. It's currently the best solution. But we just think that, if you're optimizing for longevity, cost, and safety, and you give up the density, that there has to be kind of like a better technology out there. But they're kind of it's kind of like David versus Goliath. So we're trying to get around that a bit. But understanding what people actually need in a real system and how that influences at the beginning is like super useful. So any feedback is super helpful.
Kirk, I'm Miles. My company Loft is making alternative propulsion for ships, and completely unconnected to this, I've been interested in flow batteries for that application. Don't know much about them though, so I'd love to chat.
Yeah,
Also,
no,
we can help with CAD and CFD.
Cool.
If you need that.
That's great. No, let's get in touch. There is a in the UK, there is a flow battery that has been used on a ship to, I think, help provide like shore power for docked ships without having to upgrade. And I think there's one ferry somewhere that is using a flow battery, but I don't know how long it is.
Interesting.
I think that's in the UK. Anthony Price is a UK consultant. So if you look him up, you might be able to find that project.
Cool.